Welcome to The Deep Dive, the show where we slice through the noise and get straight to the essential insights. Today, we're plunging into a topic that sounds like it's ripped straight from a cyberpunk novel, but is rapidly becoming a tangible reality: human body communication. Seriously, imagine your fitness tracker, your smartwatch, and maybe even a future implantable health sensor all talking to each other. But not through the air using Bluetooth or Wi Fi, no, through your own body. That's right, we're talking about using you as a living, breathing, secure, and incredibly energy efficient network. And let me tell you, it is far more fascinating and maybe a bit more complex than you might initially think. Our mission today is to unpack a truly groundbreaking paper. It's titled Biophysical Modeling, Characterization, and Optimization of Electroquasistatic Human Body Communication. Woo, that's a mouthful. But this deep dive isn't just about understanding some cool piece of tech, It's really about solving some long-standing, really quite vexing mysteries that have held back this whole field for years. We're going to show you precisely how researchers are figuring out how to turn you into a living communication channel and revealing its hidden potential. We'll explore how this incredible technology works, why it actually matters, and what it could mean for the future of all those wearable and implantable devices that are, well, quickly becoming indispensable parts of your daily life.
Yeah, and what's truly fascinating here, you can see it right from the abstract, is the core elegant idea, using the human body itself as the communication channel for these tiny low-power devices. It presents a really compelling and frankly quite ingenious alternative to traditional radio wave communication. It promises not only, enhanced energy efficiency, but also a level of inherent security that's just hard to achieve with signals flying through the air. But here's the rub, and it's been a significant roadblock for a while now. Previous research in this area has been, well, let's just say a bit of a Wild West. We've seen hugely varying, often contradictory results. One study says one thing, another says the opposite. And that's made it incredibly difficult for engineers to actually design and build reliable HPC systems. You need consistency. This paper, though, with its meticulous biophysical modeling and really rigorous experimental validation, it aims to bring much-needed order to that chaos. It's about taking the guesswork out of how your body truly transmits these signals. That's basically providing a unified, dependable map for this really complex territory. Finally.
And what a map it is. This paper isn't just, a small step forward. It feels pretty revolutionary in its clarity. We're going to discover how understanding even the most subtle differences in how you measure things like something technical sounding, like termination impedance, right? Which essentially describes how a device listens or loads the signal, how understanding that can dramatically alter our entire perception of how well the body communicates. We're talking about differences, variations up to 4 dB just by using different oscilloscope probes. And then an even more significant 9 dB additional channel loss when you measure it with a proper miniaturized wearable prototype compared to that oscilloscope.
That difference is huge for designers. Absolutely massive.
Exactly. And here's where it gets really interesting, I think, and fundamentally changes our understanding. It's the surprising pivotal role of capacitive termination. This specific way of receiving the signal seems to create a remarkably flat band communication channel, flat response, and it extends all the way down to an incredibly low 13 kilohertz.
Which is remarkable.
It really is. This definitively establishes the human body as a viable, not just for some niche things, but a truly broadband communication medium. It can handle higher data rates. So what does all this meticulous, groundbreaking research actually mean for you, the person wearing or maybe someday relying on these future devices? How will it change your interactions with technology? Let's dive in. Meta 1, the dawn of human body communication, HBCC. Why your body is the next big network. Okay, let's unpack this concept then. Human body communication, or HBC. For over 5 decades now, we've seen this incredible technological revolution, Moore's Law, right? It's relentlessly shrunk the size and the cost of computing components. Everything gets smaller, cheaper, faster. And this continuous miniaturization has led to an explosion of tiny, sophisticated devices that we now wear or, that we're starting to see implanted inside the body. Think about everything from the smartwatches tracking our activity, the continuous glucose monitors giving vital health insights, or even more advanced to the futuristic health sensors designed to live inside the body, maybe monitoring neural activity or organ function. It's amazing stuff.
Right. And these aren't just isolated gadgets floating around. They need to talk to each other, or talk to a central hub like your phone, or even to external medical equipment. They form what's increasingly called a body area network, or BAN.
A BAN, okay.
Yeah. And the sheer volume of data these devices could generate precise heart rate variability, detailed sleep patterns, continuous glucose levels, oxygen saturation, neurological signals, maybe even early biomarkers for disease. It's immense. It's a flood of data. And for this torrent of personal health data to be truly useful, to be actionable, it needs to be communicated efficiently, reliably, and maybe most importantly, securely. Now, traditionally, devices within a band have relied on, well, conventional radio waves, like the Wi-Fi connecting your laptop or the Bluetooth linking your headphones, standard stuff. But the human body, it turns out, with its remarkably good conductive electrical properties, offers a far more intimate and potentially orders of magnitude more efficient way for these devices to connect. It can literally be the communication channel itself.
Using the body as the wire, essentially.
Pretty much, yeah. The core advantage of HPC lies in this promise of vastly greater energy efficiency. Compared to traditional wireless media, HPC exhibits significantly lower channel loss.
Okay, what does that mean in practical terms? Lower loss means.
It means less power is needed to transmit a signal from one point on your body to another. Simple as that. Now think about the power budget of a tiny wearable battery. These devices are often sleek, small, meant to be worn for days, weeks maybe, without a recharge. Every single millijoule saved in communication significantly extends that battery life. And that's absolutely critical for user experience, for convenience, and frankly, for the viability of these technologies.
Especially for implants, I imagine.
Oh, absolutely. For implantable devices, which often require surgery to replace their power source, extending battery life from, say, a few months to potentially several years, that represents a monumental leap in quality of life. It reduces patient burden, cuts healthcare costs. This isn't just a marginal improvement we're talking about. It's a fundamental shift in how we power and sustain these tiny, sometimes life-changing technologies.
Right. And beyond the crucial energy savings, one of the most compelling advantages, as the paper really points out, is security. HBC signals operate with larger wavelengths compared to typical radio waves like Wi-Fi or Bluetooth. And this translates to lower radiation, which is good, but crucially significantly enhanced physical layer security. What does physical layer security really mean for you, the listener? It means that if the signal is primarily contained within your body, it becomes astronomically harder for some attacker outside your body to snoop or intercept or interfere with those signals.
It's naturally confined.
Exactly. Imagine a world where a secure authentication key for your car or your smart home or maybe even your digital wallet only works when the device is physically touching you, making a secure connection through your body's inherent conductivity. This is huge for protecting highly sensitive health data flowing from medical implants, ensuring privacy, or creating entirely new forms of secure personal access that are intrinsically linked to your physical presence.
Your body literally becomes its own secure, self-contained network. It adds a layer of physical security that traditional over-the-air wireless methods just can't easily match.
It's almost like an unforgeable form of authentication.
So what does this actually enable? In terms of real-world applications today and, in the very near future, the paper points to some pretty transformative possibilities that go way beyond just simple fitness tracking. We're talking about advanced wearable health monitoring, where continuous real-time physiological data can be collected with, well, unprecedented accuracy and security. Think beyond steps. Imagine continuous high-res sensor data flowing seamlessly from multiple patches on your body, providing advanced diagnostics for chronic conditions, maybe even predictive analytics for acute health events. And this data, all securely transmitted within your personal body network, could be vital for personalized medicine.
That's powerful.
It also allows for seamless kind of intuitive information exchange between wearables. Maybe you could exchange contact info or digital assets with a simple, secure handshake. Your body's acting as the temporary, secure conduits.
Wow, like a digital handshake.
Sort of. Or consider unlocking your car or accessing a secure building just by touching the door handle with a specific wearable. Your body completes the secure circuit for the authentication signal. The potential for secure authentication using a body-worn key is a really recurring, exciting theme in this research. It highlights how HPC can make our tech interactions more intuitive, more seamless, and far, far more protected.
Okay, so the paper focuses specifically on what's called capacitive HBC, right? And you mentioned there are two main flavors. Can you quickly clarify the difference?
Sure. So in capacitive HPC, which is our focus today, the signal is coupled into your body through just a single electrode. Think of it like one tiny antenna touching your skin. The return path for the electrical signal isn't another electrode touching you somewhere else. Instead, it's formed by the capacitive coupling of your body with the earth, ground, and, other surrounding objects. It's a bit subtle.
Okay, so one contact point, and the return path is sort of ambient, through capacitance to the environment. Essentially, yes. The other main type is galvanic HBC. That uses a differential signal applied via two distinct electrodes on the body. And the signal is picked up as a potential difference between another pair of differential electrodes. Both have their merits, definitely. But we'll be diving deep into capacitive HBC because that's where this particular paper makes its most significant contributions. It really changes our understanding of its capabilities and opens doors for future device design.
More. The challenge of understanding HBC. Why previous studies left us scratching our heads.
Okay, so if human body communication is so promising, right, it boasts all these incredible advantages, energy efficiency, security. Why aren't we seeing it everywhere already, in every new watch or sensor? Well, you touched on it earlier. The research community has been grappling with this fundamental and frankly pretty frustrating issue for years, which is that previous study trying to actually measure the body channel reported wildly varying, often contradictory results. If you look at Figure 1 in the paper, we'll link to it. Of course, it's a visual representation of how, well, all over the map the results have been. It's messy.
It really is. Some studies showed minimal signal loss, making it look fantastic. Others reported prohibitively high loss, suggesting it's not practical. Some claimed a flat band response, great for broadband data. Others showed a narrow bandpass characteristic, which would severely limit data rates.
Right, and this kind of inconsistency makes it incredibly difficult, almost impossible, to design reliable and robust HBC systems. If you're an engineer, how do you even begin to build a device when you don't know if the communication channel is like a superhighway or a tiny bumpy back road?
Exactly. It's like trying to build a bridge without knowing if the riverbed is solid rock or shifting sand.
Yeah, this uncertainty has been a major roadblock to getting this tech out there.
And you've hit on precisely why this paper is so critical, why its findings are such a breakthrough. It directly tackles that historical confusion. The authors meticulously identified two primary reasons for this wide variance as uncertainty, and understanding them is absolutely key to moving forward, to unlocking HBC's full potential. The first culprit was insufficient ground isolation. Many early measurements were done using standard lab instruments, oscilloscopes, network analyzers. The problem: these instruments are typically plugged into the wall for power.
Okay, and that matters because...
Because that connection means they inherently have large ground planes, which can inadvertently create a shared kind of artificial return path between the transmitter and the receiver. Imagine trying to test the electrical resistance of one tiny, delicate wire. If your test equipment is also connected to a huge metal plate, the ground, and that plate accidentally touches both ends of your wire, your measurement will show the plate's low resistance, not the wire's true resistance.
Okay, it creates a shortcut.
Precisely. That's essentially what happened with wall-powered lab gear. Their large, earth-grounded planes created a much easier, unintended return path for the signal. This made the channel loss look lower, sometimes significantly lower, than it would actually be in a true, isolated, real-world wearable scenario, where devices are small, battery-powered, with tiny, isolated ground planes.
So researchers were getting an overly optimistic reading, one that didn't reflect reality.
Exactly. An optimistic reading that simply didn't match how these devices would operate when you're actually wearing them.
Right, it's like measuring the speed of a car, but secretly it's rolling downhill. You think it's fast, but the conditions aren't real. Okay, so that's one issue. What was the second major problem the researchers identified?
The second issue is about how the signal is received, or technically terminated at the other end. Many previous studies use standard lab instruments like vector network analyzers, VNAs, or spectrum analyzers, and these typically have a very specific standardized low input impedance, 50 ohms. 50 ohms.
50 ohms. Okay, why is that low impedance a problem here?
Well, it drastically affects the measurements, especially at lower frequencies. Think of it like trying to measure water flow in a pipe again. If your measuring device itself acts like a huge, wide-open drain that's like the low 50 impedance, it fundamentally changes the pressure and flow you're trying to measure. This low impedance leads to artificially higher voltage loss at low frequencies. It gives a misleading high-pass response, making it look like low frequencies are filtered out or severely weakened.
So it made people think HBC wasn't good for low frequencies, therefore maybe not good for broadband.
Precisely. It made many believe HBC was only suitable for narrowband, maybe higher frequency signals. So this paper sets out to unequivocally clear up these discrepancies. First, by developing a unified biophysical model, and then by recommending optimal, validated measurement techniques, essentially giving us a consistent, accurate ruler to finally measure the body's true communication capabilities. 3. Unpacking the human body as a communication channel, a unified biophysical model.
Okay, so before we dive into the model itself, this sophisticated blueprint they built, let's just quickly touch on the fundamental physics again. The paper focuses meticulously on frequencies up to 1 megahertz. Why is that specific frequency range so important?
Because at these frequencies, we're operating in what's called the electroquasistatic regime, EQS for short. What that means is the signal wavelength, which is huge, over 300 meters at 1 megahertz, is vastly, vastly larger than the human body itself, maybe 2 meters tall on average.
Okay, huge wavelength compared to body size. Got it.
Right. And this enormous scale difference is crucial. It means magnetic fields don't really contribute significantly to conduction within the body. The signal is primarily contained and travels via electric fields rather than propagating like complex radiating radio waves in the air. We're dealing with electric potential distribution across a conductive medium. And the beauty of this EQS approximation from an engineering standpoint is that it simplifies the modeling dramatically. It makes the problem much more manageable. The paper rigorously shows the approximation error at 1 megahertz is incredibly tiny, like 0.05%. In fact, the EQS model holds up pretty well, staying valid all the way up to nearly 10 megahertz.
Wow, okay.
So this means we can accurately model the electrical behavior of the body as a communication channel using much simpler circuit elements, resistors, capacitors. We focus on electric field dynamics, not complex electromagnetic wave equations. It lets engineers treat the body like a circuit, not an antenna.
That simplification must be huge for designing small, power-efficient devices.
Absolutely paramount. And remember, the outer layer of skin, the stratum corneum, it's relatively high impedance, kind of like an insulator. So the signal primarily travels through the underlying, more conductive layers. The dermis, connective tissue, muscles, fat. Think of your skin as a slightly insulating sheath, and the, well, gooey, salty interior of your body as a lossy wire, a conductor, but one that weakens the signal a bit.
Okay, the gooey bits are the main path.
Pretty much. And understanding that is crucial because it tells you how electrodes should be designed to effectively couple the signal into and out of the body, bypassing that most resistive outer skin layer.
Right. So building on this understanding EQS regime, conductive inner layers, the researchers developed this simplified or lumped circuit model. It's shown in Figure 2B in the paper. It's like creating an electrical blueprint of your body's communication pathway, right? Condensing complex physics into manageable circuit bits.
Yes, exactly. The model includes crucial components like the electrode-to-skin contact capacitance, they call it C-band. It can be hundreds of picofarads if the contact is really tight, like less than a 0.1 millimeter gap. Then there's the skin impedance itself, typically in the Coulomb range, acting as a barrier. Below that, you've got the internal fat and conductive tissue impedance, much lower, maybe hundreds of ohms. That's the main signal pathway.
Okay.
The model also accounts for the transmitter's source impedance, usually just a few ohms. And, very importantly, the receiver's load impedance, which, as we've discussed, can vary wildly depending on the equipment.
Like the oscilloscope probes having high resistance, but also some capacitance.
Right, and what's particularly insightful and often missed before is that this model also incorporates parasitic capacitances. These are unintended but very real capacitances formed between your body and the device ground planes, and even between your body and the earth ground itself.
Ah, the subtle environmental effects.
Exactly. These seemingly minor, unintended electrical interactions actually have a huge impact on the overall channel characteristics. Failing to account for them accurately led to many of those past discrepancies. Indeed. And the credibility of any model, especially one trying to unify decades of conflicting results, depends on how well it reflects reality. So how do you get the actual real-world values for these components in the model? They didn't just guess. The team ran specific, quite clever experiments to precisely estimate each critical parameter. For instance, to accurately pin down the return path capacitance, which we now realize is a major player in signal loss, they did something neat. They added known, precise capacitances between the transmitter and receiver grounds and meticulously measured the resulting signal loss. That's detailed in Figure 3.
Okay, so by adding knowns, they could calculate the unknown capacitance.
Exactly. By doing this, they estimated the return path capacitance to be tiny, around just 1.5 picofarads. But this crete is incredibly critical because it represents the primary source of overall channel loss in a real-world non-common ground scenario. It's not the body's internal resistance like many assumed. They also needed to estimate the body-to-ground capacitance, see body drained, how your body couples capacitively to your surroundings. For this, as shown in Figure 4, they applied a known signal to the body through a series resistor and watched the characteristic time constant on an oscilloscope, how quickly it charged and discharged through the body's capacitance to ground.
Like an RC circuit measurement.
Precisely. By comparing the time constant with and without the body in the circuit, they determined this capacitance to be about 150 picofarads. And since this is the total capacitance from the body to the earth ground, it's logically split between the transmitter and receiver ends in their comprehensive model.
Wow, okay, so they built this really detailed model and then experimentally validated each key piece.
That's right. With this robust, experimentally validated biophysical model, incorporating these carefully derived parameters, we can finally characterize the body channel with much greater accuracy and consistency. It paves the way for reliable broadband communication because we finally understand these fundamental electrical properties. 4. Broadband communication. The body as a lossy wire.
Okay, so we've talked a lot about understanding the body channel, modeling it, measuring it accurately up to 1 megahertz. Why is that particular frequency range, that bandwidth, so critical? Why the focus on 1 megahertz?
Because that kind of bandwidth isn't just a technical detail. It unlocks the door to truly broadband communication through your body. It allows for significantly higher data rates than traditional narrowband approaches could ever achieve.
Right, broadband means faster data.
Yep. Exactly. To put it in perspective, a 1 megahertz bandwidth can reliably support up to about 1 LDP's 1 megabit per second data rate. And that's more than enough for many crucial HPC applications. Things like continuous high-resolution physiological health monitoring that needs a steady, rapid stream of data, or incredibly fast and secure authentication protocols that need almost instant verification.
Yeah, you can't wait seconds for your door to unlock.
Right. Think about the historical difference between an old dial-up modem, very narrow band, painfully slow, and modern fiber optics broadband, incredibly fast. For your wearable devices, this means faster, more fluid data exchange. Imagine continuous high-res sensor data flowing seamlessly and instantly from multiple points on your body for advanced diagnostics, enabling earlier detection of health issues or more precise, real-time adjustments to medical treatments. This leap to broadband is what truly unlocks the potential. Absolutely. And another colossal advantage of true broadband HPC is its inherent efficiency. It comes from a fundamental design simplification. It essentially bypasses the need for complex, power-hungry modulation and demodulation circuits. Those are typically required in narrowband wireless communication.
Ah, the encoding and decoding stuff.
Exactly. In traditional wireless, you have to encode your data onto a carrier wave, transmit it, then the receiver has to decode it back. That whole process, involving intricate signal processing and RF components, it consumes a lot of power. By directly utilizing the complete bandwidth of the body for transmitting the raw data, broadband HPC becomes profoundly more energy efficient, potentially achieving an incredibly low energy consumption, maybe down to 6.3 picojoules per bit transmitted.
Picojoules? That sounds incredibly tiny.
It is. That's orders of magnitude less power than traditional wireless. It makes it an absolute game changer for devices with severe energy constraints, which, let's be honest, is practically every tiny wearable and implantable device you can think of.
Right, longer battery life, smaller devices, less charging. It all comes back to that fundamental efficiency. The paper does a fantastic job illustrating this difference, narrowband versus broadband, in terms of how signals are actually sent and received. That's in Figure 5. In narrowband, the goal is often about efficiently transferring power, right? And channel characteristics are measured as a ratio of received power to transmitted power.
Right.
But broadband, as the paper details, it operates differently. It sends signals as direct voltage corresponding to ones and zeros. That's called voltage mode signaling.
Yes, voltage mode. It's a key concept here.
So this means for designers building your next-gen wearables, they need to understand the channel not just in terms of power loss, but much more critically in terms of voltage loss.
That shift in perspective is absolutely critical for designing effective broadband HPC systems.
Okay, so now that we understand the why of broadband and the how of voltage mode signaling, let's tackle those frustrating measurement discrepancies head on. Let's see how this paper finally clears them up. 5. Solving the measurement maze. New approaches and insights.
Right. So to truly understand where the communication loss actually comes from in HPC, the researchers first took this really brilliant step. They eliminated one of the biggest variables that had historically confused things, the return path capacitance we talked about. They did this by conducting common ground measurements. They effectively shorted the grounds of the transmitter and receiver together. That's shown clearly in Figure 6.
Okay, common ground. Why was that strategically important?
The motivation was profound. This setup allowed them to characterize only the forward path loss, the loss occurring within the human body itself, completely without the confounding, often misleading effects of the return path. It isolates the body's intrinsic performance as a conductor.
Got it. Measuring just the body, not the whole loop, including the return path.
Exactly. Their experimental setup was pretty straightforward. A signal generator provided a precise sine wave, an oscilloscope measured the receives voltage, and the grounds of both instruments were directly connected. Simple, clean. Now, what's truly fascinating are the results from this common ground test. They're presented clearly in Figure 8, the forward path channel loss. It was found to be remarkably, surprisingly minimal.
Really? Minimal loss through the body itself.
Yeah. For a single-ended setup signal referenced to one ground point, the loss was almost negligible, like around 0 dB, barely any loss. With differential excitation signal on two opposite polarity wires and single-ended termination, it showed about 6 dB of loss. Still not huge. And with differential excitation and differential termination, it resulted in about 10 dB loss.
So wait, the big takeaway here is the body itself isn't that lossy?
That's the aha moment. It unequivocally showed that the human body's internal conductive layers are actually quite efficient for signal transmission, at least over these typical body distances. This fundamentally overturns a long-held assumption that the body itself was a major signal attenuator, a big hurdle for HBC.
Wow. So we were blaming the body, but it wasn't the main culprit.
Not the main culprit for the overall loss, no. It reveals the body's surprising inherent efficiency. This means that most of the overall loss in HBC, therefore, doesn't come from the body itself, but overwhelmingly from the non-common ground return path capacitance. And even for this intrinsic forward path, how you excite and terminate the signal single-ended versus differential still makes a difference.
Okay, so if the body isn't the main loss source, then understanding and accurately measuring the return path and the whole setup is absolutely critical.
Precisely, which leads us directly to the next crucial set of experiments they performed.
Right. That insight is a total game changer. It means we were potentially barking up the wrong tree for years. Okay, so now let's turn to the core of those previous discrepancies, the non-common ground scenario, the realistic one. In a real-world wearable situation, your devices don't share a common ground. They're not plugged into the wall. So the return path becomes this profoundly crucial factor that absolutely needs to be accurately characterized. To investigate this, the researchers used two different setups. First, they used an oscilloscope-based setup. Now, the scope has a large ground plane because it's plugged in, which we know can be an issue.
Right, potential source of error.
But they used it very carefully with precisely controlled high-impedance probes. As shown in Figures 9a and 10, they used a battery-operated miniaturized signal generator as the wearable transmitter, mimicking a real device, and the oscilloscope as the receiver. And they specifically used high-impedance probes to provide that capacitive termination at the receiver end.
They tested two different probe types to see the effect. A 10x probe, that's 10 megohms resistance in parallel with a low 13 picofarads capacitance, and a 1x probe, which is 1 megohm resistance in parallel with a higher 79 picofarads capacitance.
Okay, so what did they find with this oscilloscope setup? The results are in Figure 14.
Well, the measured channel response was indeed flat band over frequency, which was a good sign, confirming the potential for broadband communication. The channel loss for the 10x probe was measured around -43 dB, and for the 1x probe, it was a bit higher, around -47 dB, which makes sense. Its higher load capacitance leads to slightly greater loss.
Okay, flat band, around -40s dB loss. Seems okay, but there's a catch, right?
There's a critical catch, yes.
Yeah.
And the authors are very clear about this. While these measurements appear to show a flat band response and reasonable loss, oscilloscopes, because they're wall-powered, inherently have those large ground planes. This artificially inflates the return path capacitance to the earth ground. It creates an easier than realistic return path for the signal.
Back to that shortcut problem.
Yes, exactly. This leads to an optimistic, meaning lower than actual estimation of HBC channel loss. It makes HBC look better than it truly performs in an isolated, battery-powered, wearable-to-wearable scenario. Precisely. It means many earlier studies might have unintentionally painted an overly rosy picture of HBC's performance in the real world, just because of their lab equipment. A profound insight that clears up so much confusion. So, to get an accurate, truly representative picture, the researchers then moved to their second and most crucial setup, the miniaturized wearable prototype-based setup. This is as close as you can possibly get to replicating a true wearable-to-wearable communication scenario.
The real deal.
The real deal. As illustrated in figures 9b and 11c, they actually built a completely battery-operated miniaturized receiver with a small, isolated ground plane. This design mirrors how your actual devices would communicate on your body in everyday life, free from those confounding factors of big lab equipment grounds.
Okay, but building a tiny receiver is one thing. How did they actually measure the broadband signal? Up to 1 megahertz with presumably simpler, lower power electronics inside that prototype.
That's where they got incredibly clever. This wearable receiver performs voltage mode sensing, right? So it uses an ADC, an analog to digital converter, to sample and digitize the received voltage waveform.
Okay.
Now, a standard, say, 1 MSPS ADC, 1 million samples per second, would normally limit your accurate measurements to maybe around 100 kilohertz if you want good signal reconstruction, not the full 1 megahertz bandwidth they needed to see.
Right, you need to sample faster than the signal frequency, microspirum and all that.
Exactly. But instead of using an incredibly fast, power-hungry ADC, they employed a brilliant histogram-based approach. It's visually explained in Figure 12. Instead of trying to capture the entire high-frequency waveform in real time, they used a simple square wave input signal and then randomly sampled it at a lower rate with their 1 MSPS ADC.
Randomly sampled a square wave. Okay, how does that help?
By creating a histogram, basically, a statistical plot of the differences between consecutive samples taken over time, they could accurately infer the signal's amplitude and characteristics across the full 1 megahertz bandwidth. Even though the sampling rate was lower than the signal frequency, it relies on the statistical distribution of those differences.
Wow, that is clever. So they could see the broadband picture with slower hardware.
It's a truly ingenious workaround, a testament to smart engineering. It allows characterizing broadband signals with simpler, lower-power hardware, making real-world implementation in tiny, battery-constrained devices much more feasible. And of course, the raw data from that wearable receiver wasn't the pure channel response yet. This prototype receiver had an internal amplifier, gave it a gain of 12, and a bias circuit, both of which naturally affected the raw signal measurements. So they meticulously de-embedded these known circuit characteristics from the raw measurements. They mathematically removed the amplifier's effect to isolate the true channel response, getting the body's performance separate from the device electronics.
Right, peeling back the layers to see the core channel.
Exactly. After all that meticulous processing and careful calibration, the results, shown in Figure 15, were, again, flat band over frequency, reinforcing the broadband potential.
Okay, flat band again. But what about the loss? Was it the same as the scope?
No. And this is the crucial distinction, the vital finding for designers. The channel loss in this realistic miniaturized wearable scenario was significantly higher. It ranged between -49 dB to -52 dB.
So roughly 6 to 9 dB more loss than the oscilloscope measurements suggested.
Precisely. This definitively shows that oscilloscope measurements, while useful maybe for initial checks, provide an optimistic estimation of channel loss because of their large grounds. True wearable-based measurements reflecting real-world conditions are absolutely essential for accurate characterization. They give designers the real performance metrics they need.
This is incredibly important. It tells engineers how much signal strength they really need to build into your devices for reliable communication, to make sure your next-gen wearables work consistently in everyday life, not just look good in a lab test. 6. The blueprint for better body communication, optimizing HBC signaling. Okay, so after all these insightful experiments, the detailed modeling, finally clearing up decades of measurement confusion, what's the big actionable lesson here? How do we make human body communication work effectively and reliably for you in future devices?
Well, the first and perhaps most critical takeaway is avoid 50-38 termination at the receiver. Full stop. This is the classic pitfall of using traditional lab instruments for HPC, and it fundamentally misrepresents the body channel.
Right, the standard impedance for RF gear, but wrong for HBC.
Exactly. Many previous studies use VNAs or spectrum analyzers, both typically having that standard 50A input. Here's why it's a problem again. The human body channel impedance is usually in the range of several kiloohms, thousands of ohms, much higher. Using a mere 50A termination, as Figure 16 dramatically illustrates, results in very high voltage loss. Why? Because most of the signal voltage simply drops across the body itself, which has much higher impedance rather than being effectively transferred to that low impedance receiver.
It's like a massive impedance mismatch, wasting the signal voltage.
Precisely. It's like trying to power a high-resistance light bulb. Using a measuring device that acts like a short circuit, you just won't see the bulb's potential. This incorrect setup leads to a pessimistic, exaggerated estimation of channel loss. especially at low frequencies. It makes HPC seem far less viable than it actually is.
So many earlier studies basically misjudged the body's potential just because of their test equipment impedance.
That seems to be a major factor, yes. So instead, for accurate voltage mode measurements, which again are essential for broadband data, we absolutely need a high impedance termination at the receiver end
High impedance. Why again?
because it minimizes the voltage drop across the body channel itself. It ensures that more of the signal's voltage actually reaches the receiver input. Think of the water hose analogy again. A tiny, high-resistance nozzle, low-impedance receiver, wastes pressure. A wide-open pipe, high-impedance receiver, lets the pressure through efficiently. A high-impedance receiver sees more of the voltage that's actually being transmitted through your body.
Okay, high impedance is good. Less signal lost before it's measured.
Right, and crucially, a low termination resistance, when coupled with that unavoidable return path capacitance, creates a high-pass filter effect. The lower that resistance, the higher the cutoff frequency of that filter, meaning more low-frequency signals get inadvertently filtered out and lost. Figure 17 shows this clearly.
That explains the old high-pass results. It wasn't the body, it was the low-impedance termination acting like a filter.
Exactly. This perfectly explains many of those bandpass or high-pass channel responses reported in earlier, less accurate studies. And here's why this matters for you. Your actual wearable devices, built with modern CMOS technology, naturally have very high input impedances. So using high impedance measurement setups gives a far more realistic picture of how those devices would actually perform on your body. It matches the technology.
Okay, this is clarifying so much. Now, this brings us to what you said was maybe the most crucial discovery, the real game changer for broadband HBC. It wasn't just high impedance, but the type of termination. You said capacitive termination is the secret weapon.
It really seems to be the key for achieving that desirable flat band response. Yes, let's break it down. We know that purely resistive termination, especially low resistance, leads to high loss and that unwanted high pass response. That's because the return pad capacitance acts like a filter against the resistance.
Right.
But here's the aha moment. A high impedance receiver that also has capacitive termination actually results in a remarkably flat band channel response. Figure 18 shows this brilliantly.
Flat band. Why does adding capacitance help flatten the response?
Because the output voltage then effectively becomes a capacitive voltage division. It's a ratio between the return pass capacitance and the termination capacitance, C term. Since both are capacitances, their ratio is largely independent of frequency, at least at these lower frequencies. This interaction cancels out the frequency dependence that causes the high-pass filtering with resistive loads.
Wow, so the capacitance in the termination basically counteracts the capacitance in the return path.
In a way, yes. It leads to a flat response. And the impact is dramatic. This approach can achieve up to a staggering 50 dB loss reduction at low frequencies compared to using a low resistive termination.
50 dB, that's enormous.
It is. This completely definitively refutes the long-held incorrect idea that HBC is inherently a high-pass channel. Instead, it powerfully demonstrates it can be truly flat band, ideal for high-speed broadband data transmission. And importantly, this isn't just some academic curiosity or theoretical trick. This finding is also incredibly realistic and practical for modern electronics, especially for CMOS circuits, the backbone of virtually every modern chip in your phone, your watch, everything. In CMOS, the receiver's inherent input gate capacitance naturally acts as this crucial termination capacitance.
So the solution matches the technology we already use.
Exactly. This explains why many previous studies using outdated resistive measurement techniques incorrectly reported high-pass responses. And more importantly, it firmly establishes the fundamental feasibility of true broadband transmission through your body, paving the way for high-bandwidth, energy-efficient personal area networks right on and within you. Finally, just to complete the blueprint for optimization, to maximize the receive voltage in this voltage mode signaling, the receiver impedance should be as high as possible. As we said, at these low HBC frequencies, complex impedance matching isn't needed like in high-frequency RF. Simpler is better. High impedance wins. Conversely, the source impedance of the transmitter should be minimized, made as low as possible.
Low source impedance, why?
To reduce any voltage drop across the transmitter itself. Figure 19 shows this. A low source impedance ensures that the signal voltage is efficiently coupled into the body channel in the first place.
Okay, so high impedance capacitive receiver, low impedance source transmitter.
That's the optimal recipe. That's the blueprint, if you will, for designing incredibly efficient, reliable, and effective HPC systems that will power your next generation of connected devices. Outro.
Wow. What an incredible deep dive into, well, the hidden network within us. We've uncovered how the human body, operating in this electro-quasi-static regime, can serve as a surprisingly effective, surprisingly robust communication channel for our devices. We've seen how a unifying biophysical model, built on really meticulous experimental validation, has clarified previous discrepancies that honestly plagued this field for years, almost bringing progress to a halt.
It really felt stuck for a while.
Yeah. The key nuggets of knowledge from today are just so clear now. The minimal loss inherent in the body's forward path, showing the body itself, is actually a much better conductor than we thought. The critical, often misunderstood role of the non-common ground return path in contributing most of the overall channel loss. The dramatic, game-changing impact of termination impedance, especially capacitive termination on getting accurate measurements and achieving flat response, and the absolute necessity of doing real-world wearable measurements for true, unbiased characterization, not just relying on lab scope.
Absolutely essential.
And crucially, we've learned that a high capacitive termination at the receiver paired with a low source impedance at the transmitter, that's the optimal setup. That's the foundation for making your body function as a remarkably efficient lossy wire for true broadband communication.
And let's be clear, this isn't just academic research locked away in a lab somewhere. These findings have profound, tangible implications for you, the everyday user of wearable and implantable tech. By truly understanding and meticulously optimizing human body communication using these principles, engineers can design devices that are far more energy efficient. And that translates directly to significantly longer battery life for those small, sleek, energy-constrained devices you rely on daily. Less charging, more seamless use. That's huge.
Definitely a big win for users.
And this optimization isn't just about convenience. It fundamentally paves the way for advanced remote health monitoring, where continuous high-resolution and supremely secure data is vital for managing chronic conditions, enabling preventative care, maybe even delivering personalized medical interventions in real time. It also opens up those exciting possibilities for secure authentication methods, leveraging your own body as an unforgeable living key for unlocking devices, accessing sensitive information, fundamentally changing how we interact securely with our digital world.
So as these groundbreaking technologies continue to advance and, your body becomes an even more integral part of your personal area network, what are the broader implications? How will this change how we interact with our digital world? What new forms of data privacy and security will emerge when the network is literally you? And how might this intimate connection between body and device redefine our perception of personal space, digital identity, maybe even the boundaries between our physical selves and our digital selves? Lots to think about there. We invite you to consider the exciting possibilities and perhaps a few of the profound challenges of living in an increasingly connected, body-centric future. Keep learning, keep exploring, and we'll see you on the next deep dive.